So good morning to all of you. I'm Dipankar Bhattacharya. I work at the Inter-University Center for Astronomy and Astrophysics. And the organizers invited me to give this set of pedagogical lectures on stars and their evolution in this forum, for which I'm thankful. And I hope you will get something useful from these lectures. The forum is compact star in QCD diagram. However, in these lectures, we will be discussing a lot of the basic stellar theory, not necessarily compact stars. It will lead up to compact stars towards the end. And we'll mention the relevance of QCD in that context towards the end. The rest of the time, we will spend just getting ourselves familiar with regular stars and how to go about understanding the structure of stars and how these stars eventually evolve and then give rise to compact stars. So let's begin. So if you go to a dark place and look up at the sky is clear, you will see thousands of stars in the sky. And these stars, as you can clearly see, are self-luminous objects. And what they are basically self-gravitating globes of gas, which are supported by thermal pressure of gas, which is inside it. If you leave it to gravity alone, then gravity will try to squeeze the gas globe and make it as small as possible. So you need an opposing force to keep the star of the shape and size it is. It is true for any self-gravitating object, including the Earth, where the gravity of the material of the Earth is balanced by the solid-state forces, particularly originating from Coulomb repulsion. In case of stars, of the garden variety stars that we see, this support against gravity comes from primarily thermal pressure of gas. There are fractions of other forms of pressure which also add to it. One is the pressure of radiation itself. When you have something hot, the gas is mixed with radiation, and the photons themselves exert a pressure. So that pressure plus the thermal pressure of gas is the primary source of support for the regular stars. And as you will see, as the star goes through its advanced stages of evolution, other forms of pressure will come into play, and we will see the transformation of this regular star into something else like compact stars. Now, when you have thermal pressure as the source of your support, to keep it stable, the thermal pressure needs to be immutable. It needs to stay there. However, if you have a hot object like the star, which is embedded in space outside, where the temperature is much lower, there is no way to keep the heat in. The heat will leak out. And so heat leaks out in radiation. And it is this radiation that we actually see. But as we see this radiation, it means that the internal energy, which is providing thermal pressure, is leaking out in this form. So thermal energy is lost in radiation. So if thermal energy keeps getting lost, then obviously the star cannot stay as it is for a long time, unless the energy that is lost is replenished somehow by energy generation processes within the star. And for most of the stars that we see, most of the bright stars that we see, this actually does happen. And this replenishment comes from nuclear fusion near the center of the star. And this nuclear fusion then produces energy by making the material more tightly bound, and the binding energy released in the process is converted into the thermal energy of the star. And that production rate of energy of nuclear fusion exactly balances the radiation that is leaving the surface. And when that condition occurs, you have a star which is stable in its structure for as long as this can continue. Now, as you all know, nuclear processes like nuclear fusion will give rise to gamma ray photons. But these gamma ray photons do not directly escape the star. They interact with all the material that is surrounding the core where the nuclear fusion is occurring. And interaction of these photons with this material heats up this material and also degrades the radiation that finally escapes the surface into optical photons. So you see mostly optical light from these nuclear burning stars. Now, to study these stars, one kind of diagram has proven very useful over time. And this is a diagram which can be constructed purely from observation, where on the horizontal axis, we plot what is called the color index of the star. So you take two filters, you put them on your telescope. One is a filter that allows blue light through. Another is a filter that allows slightly longer wavelength, which we call visible band. So one blue band, one visible band light through. These are two different bands of electromagnetic radiation. And we measure the intensity of the star in these two bands. When we take the ratio of these two intensities, then it tells us something about the spectral shape of the star, spectral shape of the radiation that is emanating from the star. And this is called color index. And B minus V, because this is now represented in logarithm. And once you take a logarithm of intensity, then with certain units, we call this magnitudes. So B minus V in magnitude is just the ratio of intensity that we record through the blue filter and the visible filter. So this gives you an estimate of the spectral shape. So we call it color. And on the vertical axis, what you plot is the actual amount of radiation that we are receiving from the star, let us say in V band. So the amount of intensity that we actually record through the V band. Then we, once we have a measure of the distance to the star, and the distance to the star for many of them can be obtained through what is called parallax. So, for example, the Earth goes around the sun once a year, and as we go around the sun, the distant objects tend to move in our field of view slightly. It is like when you're in a vehicle and you are driving through some forest, then you will see that the trees will tend to pass you by, and the further away the tree is, the slower it will appear to pass you by. And this is exactly the principle that is applied to the small shifts of position that we see as the Earth goes around the sun, and this is cyclic. And with that measure, one can measure the distance of this to the star. And there have been dedicated satellites to measure these distances. Hipparcos was one of the satellites, which was about a couple of decades ago. And currently, there is another satellite, much more sensitive. It's called Gaia, which is gathering data for parallaxes. So once we have a parallax, we have the distance, and we have measured the amount of radiation we receive. And when we then couple it with the distance, we can then estimate the total amount of radiation that is leaving the star. And this is in the logarithmic unit. It is called an absolute magnitude. And what is plotted on the vertical axis is the absolute magnitude. So this is a measure of luminosity. So, so this is a measure of log luminosity, which is on the vertical axis. And the color index on the horizontal axis is, as I said, related to the spectrum of the star. And the spectrum of the star, these are basically Planckian spectra, so black body spectra. So therefore, the spectrum of the star is related to the temperature. And one can calibrate this relation from observations. If you look at the color index B minus V, that can be directly related to the surface temperature in Kelvin. So once you read off color index, which is measured observationally, you can then infer what the temperature of the star is. So what you have on the horizontal axis, therefore, is a measure of temperature. And given the inverse relation between color index and temperature, in this diagram, temperature goes from right to left. So that's very well. So we have a whole lot of stars for which these can be measured. And then you see that a large fraction of stars do not sort of occupy the whole region of the diagram uniformly, but fall in a very small, narrow band, which is shown over here. And this band is called the main sequence. So the largest fraction of stars that we see around us or anywhere in the universe, you will find them located in the main sequence. This is not to say that there are no stars elsewhere. There are stars all over this place, but they are far fewer in number. So now, how do we understand this? So this can be simply understood as the fact that a star in its process of evolution moves through different parts of this diagram, depending on the mass, depending on the time. However, the largest fraction of their evolutionary time is spent on this line, which is the main sequence. And we will presently see why that is so. Now, how about our sun, which is our closest star? Our sun very much is a main sequence star, and it is located over here. It's somewhere in the middle main sequence, which relatively low mass compared to many other stars that we see in our galaxy. Stars up to about 30-40 solar mass are visible in our galaxy. And at the lower end, less than 1/10 of a solar mass stars are also seen in our galaxy. So this band actually represents the distribution of masses of stars. For a given mass on the main sequence, the star has a unique position. So if you have a higher mass star, it sits higher up in the main sequence. If you have lower mass star, it sits lower down in the main sequence. And the cause of that also we will presently see. So given that introduction to the properties of stars and how the observational properties of stars can be used to infer something about their uh, location in that diagram called the Hertzsprung-Russell diagram, and telling us something about the nature of these stars, so telling us something about what is going on and what's the evolutionary phase. Uh, to understand that, let us now go back and start try to think about how we can explain the structure of a star. Now, as we said, for most of their life, the stars are sort of stable, and where the energy balance occurs by having uh, heat lost through radiation from the surface and nuclear reactions at the center making up for that loss. And as a result, the structure of the star remains steady and stable. For such stars, we can talk about configurations that are in hydrostatic equilibrium, where there is no structural change in the star in a dynamical time. So for stars in hydrostatic equilibrium, we then have to describe it through a pressure balance. And this equation, which is written on top, is an equation of pressure balance. Excuse me. Where on the left-hand side, we have the pressure gradient. It's given a negative sign because the pressure actually goes down as R increases. So minus dPdR is a positive quantity. And on the right-hand side, you have the Newtonian gravitational constant G. This is at any radius R within the star. And this is R squared, which is that radius. M is the mass contained within that radius. So M of R is integral from 0 to R, 4 pi R squared, rho of R, rho being the mass density, dr. And that is this rho over here. And then you have these terms, 4 pi R cubed, pressure divided by c squared, c being the speed of light, and this is pressure divided by c squared. And at the denominator, you have this R squared multiplied by 1 minus 2 gm by RC squared. And this is an equation which is written in full general relativity. And it goes by the name Tolman-Oppenheimer-Volkoff equation. For the large nuclear burning stars that we just talked about, the ratio of mass to the radius, or this quantity, 2 gm by RC squared, is actually quite small. So this quantity is almost negligible for normal stars, and we can just drop this term and can have R squared at the bottom. And these other terms also, which come from special relativity, are also very small for normal stars. So these additional terms, P by C squared, is very, very small compared to the density. So therefore, we can ignore these two. And for these non-compact stars, we can use this equation, which is as you would write from Newtonian gravity. So this is hydrostatic equilibrium in Newtonian gravity. So this is a much simpler looking equation. So one is to just solve this equation to get the structure of the star. But as you can see that you cannot just solve this equation. There is a pressure gradient on the left-hand side, and it is mass, density, and radius on the right-hand side. So unless there is something to connect the pressure with density, we cannot solve this equation. So therefore, we need to supplement this equation by a relationship between pressure and density, and this relationship is called the equation of state. So once we have a relationship between pressure and density, it might involve other quantities like temperature. So if it involves other variable quantities like temperature, then you need to have one more equation to describe the variation of that quantity also through the star to close the set of equations. And in case of temperature, it is the radiation transport from the center of the stars to surface that gives you an equation to describe the distribution of temperature within the star. So using that, the equation of state and the hydrostatic equilibrium equation, one can then solve for the structure of the star. We are not going to get into the details of how we do this solution. We will discuss some examples of exact solutions of this equation. But to get a feel for what these equations tell us about the structure of the star in a very crude dimensional fashion, let us go through a very quick and simple analysis of this equation. Before we get into that, let us also look at one very important theorem that emerges from this hydrostatic equilibrium equation, and that can guide our thought regarding the structure and evolution of the stars. And this is called the Virial Theorem. Many of you are familiar with it, but I will just reintroduce it in the stellar context, where there are some additional terms and which will come in handy as we describe stellar evolution later. So we start with the hydrostatic equilibrium equation, that is dpdr minus gm of r, rho of r over r squared. We now multiply both sides by 4 pi r cubed and integrate it over the full configuration from 0 to capital R being the radius of the configuration. Left-hand side, we integrate by parts. So we integrate P of R from 0 to capital R. Now, then I will get 4 pi R cubed P of R minus integration from 0 to R, 4 pi R squared. So this is differentiating 4 pi R cubed, I get 3 times 4 pi R squared. Integrating P in dp dr, I get P dr. So this is what I get on the left-hand side. And on the right-hand side, I just have 4 pi R cubed dr. I take 1 R and cancel 1 R from here. So I get 1 by R over here and 4 pi R squared dr, gm of R, rho of R over R. Now this is now in a form which is easily recognizable. So minus g m of r rho of r over r is the gravitational potential energy per unit volume at the radius r. So multiplied by 4 pi r squared dr and integrated over the full star, this gives us the total gravitational binding energy of the system. So this is the total gravitational energy of the configuration Eg, which is a negative quantity. And on the left-hand side, we note that pressure is related to the thermal energy density of the gas. And it's in fact can be written as gamma minus 1 times thermal energy density, where gamma is the ratio of specific heats. So I can replace capital P by gamma minus 1 U thermal. So then I can take 3 times gamma minus 1 out of this integral, and I have 4 pi R squared thermal energy density at R times dr integrated. So that integral over the entire star gives us the total thermal energy content of the star. So the second term in the left-hand side becomes 3 times gamma minus 1 times E thermal. So E thermal being the total thermal kinetic energy. So put it all together and I get gravitational energy plus 3 times gamma minus 1 thermal energy is equal to 4 pi r squared P of r. So P of r is the pressure at the surface. And this is the form of Virial theorem, which is of importance to us in the context of stars. Now, when we have a fully self-standing star in vacuum, then the pressure at the surface is 0. So therefore, the right-hand side goes to 0. And we have gravitational energy plus 3 times gamma minus 1 times thermal energy equal to 0. And for gas which is monoatomic with no internal degrees of freedom, you have gamma is 5/3. So the 5/3 minus 1 gives you 2/3 here. So 3 times 2/3 gives you 2. So then left-hand side turns out to be the gravitational energy plus twice the thermal energy of the configuration, equated to 0 on the right-hand side because the pressure at the surface is 0. So this is the form of Virial theorem which will often get used in understanding the stellar structure and even the evolution of the star. We note that the total energy of the configuration is actually gravitational energy plus thermal energy. But the thermal energy itself is minus half the gravitational energy. So the gravitational energy plus thermal energy, it sums up to gravitational energy over 2, or which is minus thermal energy. So total energy is equal to the negative of thermal energy. So we should remember that, which is equal to half of the gravitational energy. So this immediately gives us a clue about one thing. So suppose I take one stellar configuration at a certain radius, which is in balance with thermal energy and gravitational energy. And then let us say I do not produce enough energy by nuclear burning. So the stellar configuration is going to change. So suppose it moves to another configuration where you now have a contraction, a smaller configuration. A smaller configuration will have a larger negative gravitational energy. So its internal thermal energy content will have to increase. So now it can find a new equilibrium at a smaller radius. So from a larger radius, it has moved to a smaller radius. In the process, both the gravitational energy and the thermal energy has increased. But the gravitational energy is negative. So therefore, the thermal energy has increased at the expense of the gravitational energy. But you can see that the thermal energy has increased only by half of the increase in gravitational energy. The other half is the amount that is radiated away. So this is also something which is very important to keep in mind. If you have a configuration where thermal energy is balancing gravitational energies, you have a steady configuration in hydrostatic equilibrium. If this configuration has to contract because of gravity, then it can only do so by losing half of its energy, gravitational energy gain in radiation. So if no radiation is allowed, then the configuration cannot collapse. The radiation has to take away half the gravitational binding energy released at any such process. So we will come to other consequences of virial theorem as we go through these lectures. Okay, so now let us come back to a rough guide to the stellar structure. So we have this hydrostatic equilibrium equation, dpdr is minus gm of r rho of r divided by r square. Now I'm going to do something very drastic because I'm only going to do something very qualitative here. Not this is not going to give you a quantitatively correct description, but it is just to give you a feel for the dependencies and dimensional estimates. So this dpdr, I'm going to make a linear approximation from the center to the surface. So at the surface, the pressure is 0. And at the center, the pressure is, let's say, PC, which denotes the central pressure. So you have 0 minus PC divided by R. That is dpdr. On the right-hand side, you have minus gm by r squared. Where I have just replaced this small r by capital R. M of r is now the total mass of the star. And rho of r, I have just replaced by average density, m by 4 pi by 3 r cubed. So this can then be rearranged to write the central pressure to be equal to 3 by 4 pi gm squared by r4. Let us rewrite this in terms of the average density. So then I will have R replaced by density. And so the rho being m by 4 pi by 3 r cubed. So then I will get the gravitational pressure in the form which is proportional to the Newtonian gravitational constant times mass of the star to the power of 2/3 times density to the power of 4/3. Okay. So this is just the requirement that this amount of gravitational pressure should be balanced. So to balance it, we need an internal pressure, which is thermal pressure in this case. So for equilibrium, this pressure needs to be matched by the equation of state. And the thermal pressure, where we have the pressure given by kT over, this is mean mass per particle, so mu mp. So if it is pure hydrogen and if it is neutral, then this would just be mp over here. But suppose it is pure hydrogen but fully ionized, then you have 2 particles per atomic mass. So then mu will be half. On the other hand, if you have a heavier nucleus like helium, then instead of so 1 particle will be of mass 4 times mp, but if it is ionized, then you will get 3 particles out of it. So this will become 4/3 mp. So mu just is there to count how many species of particles are there per atomic mass. So, so this is the expression of pressure. So now, if I take this requirement, that this central pressure, which is proportional to gm to the power of 2/3 rho to the power of 4/3 should be balanced by thermal pressure, which is given by kT by mu mp times rho, or T times rho. Then I can try to describe this in this very simple diagram, where I have log of central density on the horizontal axis, log of central pressure on the vertical axis, and G m to the power of 2/3 rho to the power of 4/3, that is pressure proportional to m to the power of 2/3 rho to the power of 4/3, can be drawn as straight lines in this diagram, where log p is proportional to 4/3 times log rho, and the proportionality constant has mass in it. So you have, for different masses, you then have these different lines which are one above the other. If you increase the mass, the line keeps its slope but just keeps going up. So this is the amount of pressure that you need to balance by thermal pressure. Now thermal pressure is proportional to Tc times density. Tc is the central temperature. So that has also a constant slope of 1. Remember, this has a slope of 4/3, and that is a slope of 1. So when you have these two, they are going to cross somewhere. And that is the place which will then represent an equilibrium, which is the equality of these two pressures. Now, where this intersection takes place now depends A on the mass of the star and B on the central temperature. So you have a whole lot of possibilities as to where this equilibrium solutions will lie, but these possibilities will be the correct possibility will be determined by the mass of the star and what is the central temperature of the star. And what is the central temperature of the star is determined eventually by nuclear fusion. When the nuclear fusion has not yet occurred, a star of a mass m, for example, will start from a very large and diffuse cloud. And due to gravity, it will keep moving along this line, the constant mass. And at any of these points, the central temperature will be such that you will have a sort of temporary balance, because the thermal equilibrium can continue longer than dynamic equilibrium. So you will have a temporary balance, but it is not something permanent. So you will, as temperature, as thermal energy leaks out, the star will slowly contract, and then it will keep moving along this line because mass is not changing. It will keep moving along the black line, and the temperature will keep rising to those values of temperature where these curves cross this line. So for example, when the star reaches here, temperature will be T1. When the star reaches here, the temperature will be T2, and so on. Now, at one of these temperatures, nuclear fusion will begin. And once the nuclear fusion begins, the temperature remains steady over there. And then that will represent the stable point of the star in this diagram for as long as that nuclear reaction stage lasts. And this is what we will see when we talk about stellar evolution. Now, the primary material, the primary fuel a star has, which it can consume to produce energy, is hydrogen. The primordial composition that a star is born with is roughly 75% hydrogen and 25% helium. And hydrogen can fuse to helium. It can burn, and it can burn at a temperature which is lower than what you would need to ignite helium, for example. So therefore, when a star is proceeding along this line and the center is getting hotter and hotter as the star contracts, and this is the consequence of Virial theorem, that as the star contracts, your thermal energy will keep increasing, so the center will keep getting hotter. And as it gets hotter, the first nuclear reaction to begin will be the fusion of hydrogen. So hydrogen will combine to form helium, and this process releases almost a large fraction of the total binding energy per nucleon that you can eventually release going to the most stable form of matter like iron. So from proton to iron nucleus is about 8 MeV per nucleon, and from proton to helium is almost about 6 MeV per nucleon. So a large fraction of the energy that nuclear fusion can eventually generate is generated in this phase, hydrogen going to helium. And as a result, in the whole lifetime of the star, this is the time that is going to be the longest lasting, because as the hydrogen burns, the star is stable in its structure, and hydrogen burning is going to produce the largest amount of energy in the entire lifetime of the star. So therefore, this is the part of the life which is the longest period in the life of the star. And now if you go back to the Hertzsprung-Russell diagram, as I had mentioned, there is a set of stars which are located in this so-called main sequence, which is the thin line in that Hertzsprung-Russell diagram. And they are there because that is their longest phase of evolution in their life. And that is the phase of core hydrogen burning. So the main sequence is therefore identified with the core hydrogen burning stage of stars. So the main sequence then has the core temperature roughly equal to the temperature, which is the characteristic temperature at which hydrogen burns, which is about 10 million degrees Kelvin. And all stars which are in the main sequence will have the central temperature more or less equal to this. There is a slight difference from lowest mass to highest mass. The temperature, central temperature increases a little bit going from lowest mass to highest mass, but they're by and large in the same bracket. So let's approximate that to be the central temperature to be defined as the hydrogen burning temperature on main sequence. So Tc is equal to Th. So the central pressure then, G m to the power of 2/3 rho to the power of 4/3 is equal to Kth by mu mp times rho. So Th being now a fixed value, which is given by the hydrogen burning temperature. So then this equation will tell you that the density inside these stars, the central density, is proportional to 1 by m squared. So this is, you get rho to the power of -1/3 on this side and m to the power of 2/3 on that side. So you get 1 by m squared. So this is interesting. So the more dense the star is, the smaller is its mass. Or the smaller the mass of the star, the lower is the central density. This also tells you that the radius of the star, therefore, will need to be proportional to the mass of the star. And once you have that, by Virial theorem, you will have the central temperature being proportional to mass over radius. And this central temperature being constant, mass over radius is constant for all the main sequence stars. So that basically defines the main sequence in terms of stellar masses and sizes. But what we measure is, of course, the luminosity and the color. So let's try and see how these relate to luminosity and color. So luminosity is the amount of energy that is escaping the star per unit time. So this can be written as the total radiative energy content divided by the radiation escape time. So total radiative energy content is this temperature inside at any given point is T, then the radiative energy density is AT to the power of 4, where A is the radiation constant. So you need to divide this total radiative energy content of the whole star by the radiation escape time. So total radiative energy content is the thermal energy plus radiative energy. So now divided by the radiation escape time. The radiation escape time is basically the number of mean free paths that a photon will travel with, the time required to travel through each of these mean free paths, the product of that. So let's small l be the mean free path. L by c is the time of flight through a mean free path. And the number of mean free paths that the photon will typically encounter is given by r by l square, because it's a random motion, r being much larger than l, right? So these are the number of encounters that the photon is going to have before escaping, and this is the time between encounter. So therefore, this gives you the radiation escape time. Now the mean free path is related to the scattering cross section or absorption cross section, and it is given by 1 over the number density of electrons or ions times the cross section, which we often rewrite as 1 over mass density times kappa, where kappa is sigma over the average mass per particle here. So the kappa is called opacity. So this product is the same as this product. So it will depend on the nature of this opacity, how it depends on density and so on, what the mean free path is. But we can rewrite this luminosity then as the total radiative luminosity a to the power of 4 r cubed. So volume. So that's roughly the total radiative energy density divided by this quantity, the radiation escape time, r squared by LC. So this is roughly A times C times L times 2 to the 4 times R. So in main sequence then, luminosity will be proportional to, because of the relation between R and M. So this is L times R. T, central temperature is roughly the same for all stars. So it's L times R. So it's proportional to L times M. And the dependence of L on density is the following. For high mass stars, the opacity comes mainly from Thomson scattering, for which kappa is actually constant. So L is therefore proportional to 1 by rho, is proportional to r cubed by m. So hence, the main sequence luminosity will be proportional to cube of the mass. For low mass stars, the mean free path is proportional to a more complex function of temperature and density. And this is because the opacity comes from typically bremsstrahlung, or free interaction between electrons and photons. So that dependence gives us, when we plug it in, we'll have a main sequence luminosity which is proportional to mass to the power of 5. But on an average then, luminosity is roughly proportional to mass to the power of 4 in the main sequence. And this also tells us that the average lifetime of the main sequence, on the main sequence of a star, is proportional to 1 by m cubed. Why is that? Well, that's because eventually the total energy content which we are using to produce this luminosity is coming from the nuclear burning of hydrogen. And the amount of fuel available is proportional to the mass of the star. So the total energy available is that fraction of the star which is actually going to do nuclear fusion. So let's call that some fraction eta. So eta times m times c squared times the efficiency of converting mass to energy through nuclear process. Let's call that epsilon. So this whole quantity is proportional to m. And you divide it by the rate at which energy is being lost, which is proportional to m to the power of 4 on an average. So therefore, m divided by m to the power of 4 gives you 1 by m cubed. So m to the power of minus 3 turns out to be the mass dependence of residence time of a star on main sequence. So therefore, high mass stars remain on main sequence much shorter than low mass stars. So if you go to a star which is 10 times the mass of the sun, its hydrogen burning lifetime is going to be 1,000 times smaller than the sun. So if we all put that all together, then we have luminosity proportional to m to the power of 4, radius proportional to m, which gives you the surface temperature being proportional to m squared, and luminosity proportional to surface temperature to the power of some high power. And when you plot that, you will get a curve like this. If you plot effective temperature now, going from right to left, this is theoretical Hertzsprung-Russell diagram. And luminosity, as you compute from this calculation on the vertical axis. So you get a steeply rising curve of luminosity as a function of temperature on the main sequence. And this red line gives you the main sequence. So main sequence itself, of course, doesn't stay as a single line, because you may start with a certain composition when the star just starts burning hydrogen, and that is called zero-age main sequence. But over time, the composition inside the star will change, because some of the hydrogen will convert itself to helium. And that change in composition, while hydrogen is still the primary burning material that is providing energy, the change in composition will cause a change in the relationship between temperature and luminosity in this diagram. So the main sequence will be a little wide here. And that's the width that you see when you go back and look at all the stars in the main sequence. It is not just a single thin strip of line, but it's a line of certain width, and that is given by the evolution within the main sequence of the star. But overall, that strip then represents all the hydrogen burning stars that are there in the universe. So, so this is how the stars which are held by thermal pressure can be described. We talked about hydrogen burning, but as the hydrogen burning completes, at some point it is possible for the star to then contract further and ignite the next level of nuclear fusion like helium, and then so on and so forth. We will come to that as we proceed a little bit further. But before we proceed, let's now introduce another source of pressure, which can be very important in both the evolution of the star, in deciding whether hydrogen burning is at all going to take place or not, or whether any other stage of nuclear burning is going to be ignited or not, as well as providing support to the final compact configurations of stars. And this source of pressure is called the degeneracy pressure. So degeneracy pressure, let's start with electron degeneracy pressure. So electrons, as we know, are elementary particles with half integral spin, h cross by 2. And these particles obey Fermi-Dirac statistics, which leads to Pauli's exclusion principles, which means that given a certain quantum state, you can populate this with only 2 particles of opposite spin and no more. Now, when the particles are in continuum, for example, they are distributed in free space within a certain volume, then we can describe this distribution using a space, which is a 6-dimensional space, 3 dimensions for position and 3 dimensions for momentum. And this phase space, which the gas occupies, can be divided into individual quantum cells of volume h cubed. And each of these individual quantum cells can be populated by at most 2 particles of opposite spin. So now let us consider a one-dimensional representation of it, where the horizontal axis is space, vertical axis is momentum, and we have this 2-dimensional phase space in this case, and we have divided this 2-dimensional phase space into small cells, and each of these cells can contain a certain contain only 2 electrons. So now if we have a certain number of electrons within this space, then I can stack it first by having the lowest momenta, and then when I have to put more electrons and I cannot exceed this distance x, because that's my confinement volume, I can only put them at a higher momentum, because I cannot pack more electrons into each of these cells. So I have to start occupying cells which lie at higher and higher values of momentum. So I build up a certain amount of momentum just by the fact that the gas is confined within a certain distance. Now, if I want to squeeze this gas now, and suppose I do not change the number of particles, but I squeeze this gas, then obviously what is going to happen is I now have to occupy and larger values of momentum, because some of these phase space cells which were available in the earlier volume have gone away. So we have to find new phase space cells at higher values of momentum, like this. So as you keep squeezing, the momentum space occupied by this gas is going to rise. So you're going to produce particles of higher and higher momentum. So the denser the material gets, the higher the momentum rises. Right? So just by the virtue of being half integral spin particles obeying Fermi-Dirac statistics, a confined gas within a volume will have a finite momentum. And the smaller the volume, the smaller the number density, the higher the number density in a given volume, the higher will be the momentum. So this we can now quantify. So let the number density of electrons be n sub e, so number of electrons per unit volume. So let's consider just an unit volume. So configuration space volume is 1. And so the momentum space volume is now let us say the momentum up to which the states are filled is Pf, where the subscript F will stand for Fermi. So I will call that Fermi momentum. So within this, the number of phase space cells is 4 pi by 3 Pf cubed by h cubed. Is 4 pi by 3 Pf cubed times 1. 1 is the configuration space volume because we are talking about unit volume. Divided by h cubed. So many cells. So twice this number of cells is the number of electrons I can put. So the number of electrons I have put per unit volume is any. So therefore, this must equal to any. 2 times this must equal to any. So this gives us a relation between the Fermi momentum Pf and the electron number density Ne. And we get Pf being proportional to h, Planck's constant, times number density of electron to the power of 1/3. Now, once you have momentum, you have pressure. Pressure is nothing but momentum flux. You take a unit area and you see how much of momentum is crossing that unit area per unit time. So if V is the average velocity of these electrons, then the pressure will be the number density of electrons times V, which is the flux, number flux of electrons per unit area. So any times V, each of them carrying a momentum P. So the pressure is simply a product of the number density times average velocity times P. So now, if all this motion is non-relativistic, then we can write V being equal to the momentum divided by mass, P by me. And then we will get pressure, the momentum being proportional to Ne to the power of 1/3, we will get pressure being proportional to Ne to the power of 5/3. Because there is one Ne, there is one Ne to the power of 1/3, there is Ne to the power of 4/3. And then V is proportional to P again, which is another Ne to the power of 1/3. So we get Ne to the power of 5/3. This is as long as V is much less than C. But as the momentum rises and velocity tends to approach the speed of light, then we cannot write V as P over ME anymore. We can substitute V by speed of light, and then P becomes proportional to Ne to the power of 4/3. Okay. So now this is electron number density, but the mass in these configurations come from ions. So which could be so the number of ions should be such that there is charge neutrality. So therefore, you have either pure protons, in which case there will be equal number of protons and electrons. You could have helium nuclei, in which case you have twice as many electrons as the number of helium nuclei, and so on. So here again, you write the effective atomic mass per electron is mu V. So the total mass per electron is mu V times MP. So the number density of electrons is related to this quantity as the mass density divided by mu V times MP. So this relation then translates this relation between pressure and electron number density to pressure and mass density. So P degenerate, so this degeneracy pressure is proportional to mass density to the power of 5/3 for electron degeneracy pressure when electrons are non-relativistic, and is proportional to mass density to the power of 4/3 when they're relativistic. So this has very important consequences. First, if we have to use this pressure instead of thermal pressure to balance a configuration, then we see one aspect of it. So we know we have to balance this gravitational pressure. So this is m to the power of 2/3 rho to the power of 4/3. And this is proportional to rho to the power of 5/3. And it changes to rho to the power of 4/3 at higher density. So as you can see, there will be certain values of mass where there will be no intersection between these lines and this degeneracy pressure line. So electron degeneracy pressure can support up to a maximum mass and no more. Again, the role of that we'll come back to in a little while. But below that mass, if the configuration finds an equilibrium where these two intersect, so you have an equilibrium point which is described by the balance between degeneracy pressure and the gravitational pressure, then the star reaches that point and is not going to go any further. Whereas in case of thermal pressure, we found that as the star loses thermal energy, it can keep going further. It can keep getting denser and keep getting hotter, and it can keep proceeding. For example, this star will come up to here, then it will halt here for a while, for as long as hydrogen is burning, because it keeps the temperature constant over here. And when that is over, it will keep proceeding forward again. But once it encounters this equilibrium, it is not going to proceed any further forward. So this provides a stable equilibrium for all time to come, unless you perturb this equilibrium by external means. So this does mean that there will be certain masses of stars which, as they contract, they come and they hit this line first before crossing the hydrogen burning line. So such stars will never be able to burn hydrogen. So such configurations will never be able to burn hydrogen. So they'll never really become a star. So we call these objects brown dwarfs. Many of them do exist. But they do not fall into the category of stars. They never burn, they never get hot enough to burn hydrogen, because degeneracy pressure stops the nuclear burning before even the hydrogen has been ignited. In some cases, you will have the hydrogen burning occurring, and then before the next burning occurs, it might be stopped. So you will get a final configuration which contains the product of hydrogen burning, but that does not burn any further. So as you can see, degeneracy pressure therefore decides how many stages of nuclear burning a star will be able to go through. And we will discuss this as we discuss stellar evolution later. So today I will stop at this point and we'll take questions, and we'll continue from here in the next lecture.
Great. Okay. Thanks a lot. It's a wonderful introduction and great lecture. So yeah, the floor is open for questions. Okay. So the first question from Surendra Padmata is, can you please explain the excluded zone and the last plot a bit more? And then there's more questions, but we'll start with that one.
Right. So the excluded zone in this central pressure, central density diagram tells you where a stellar configuration can never be. Because all stars, they are born as globes of gas which are very dilute. They're collapsing from a dilute globe of gas, which is self-gravitating, so therefore it contracts and then keeps contracting as radiation takes away energy from it. the star becomes more and more compact. The stellar configuration becomes more and more compact. So they're all starting in this diagram at far away in the lower left-hand corner. So you don't start any object on the right-hand side. So the only way they arrive in this part of the diagram is by traveling along these sloping lines. I'm assuming that now the star, this globe which is contracting has detached itself from its surroundings. So therefore its mass is not increasing anymore. So it keeps its mass constant. So all this line tells you is that its radius is decreasing, because what I plot here is the central pressure. The central pressure is just proportional to mass to the power of 2/3, rho to the power of 4/3, and rho is increasing because radius is decreasing. So motion along this line just represents contraction at constant mass. So that's what stellar gas globe is doing. So it will keep contracting, and as it contracts, the center will keep getting hotter and hotter. Some of them may get so hot as to burn hydrogen, to do nuclear fusion, and burn subsequent stages also, as we will come to later. But in many of these cases, what will happen is, as the central density is rising, the degeneracy pressure also is rising. In the beginning, as the star is moving along this black line, the temporary equilibrium is being provided by the thermal pressure, which is inside the star. But the degeneracy pressure is lurking. It rises faster than the thermal pressure. So at some point, the degeneracy pressure may rise so much as to entirely provide the support against gravitational collapse to this configuration. The reason why the star was continuing to move along these black lines while being supported by thermal pressure is that the thermal pressure is given by the thermal energy content, and the thermal energy content is leaking out. So a new equilibrium is formed as more and more thermal energy is leaked out. On the other hand, if the configuration is supported by degeneracy pressure, then that is not going to change anymore. It is going to provide eternal support to this configuration. So once the object gets supported by degeneracy pressure, it cannot move further along this black line. So therefore, the right-hand side of this blue line is really excluded for any star to enter it, because they all come from the left. And as soon as they reach this blue line, which is supported by degeneracy pressure, it cannot contract any further. So that provides a final stable configuration, which is available for eternity. So this gives you brown dwarfs if the star has not burnt hydrogen. If the star has burnt hydrogen or has gone through other stages of nuclear burning and is supported by electron degeneracy pressure, then we get configurations called white dwarfs. And we will discuss more about that in the next lecture.
Okay, thanks. There's next question is from Subhas. How does one calculate the sigma cross section? I guess they're referring to one of your previous slides where you had the sigma in the cross section.
Go back to that. We're talking about this, right? So this is scattering or absorption cross section, which is you have to compute by taking into account all processes that go on between the photon and the material. So material includes the ion, includes the electrons, and as a photon propagates, it interacts with the ions and electrons in various forms. For example, when you have an ion and an electron and radiation, they can interact by Bremsstrahlung or free emission and absorption. ion passing by, electron passing by an ion can produce radiation because of the acceleration that the ion produces of the electron. And this can generate a photon, which is called a Bremsstrahlung process. The inverse of that can absorb the photon. And that is one of the processes which is very important in stellar interiors, because the stellar interior contains mainly fully ionized gas. So you have ions, electrons. You don't have internal atomic processes very much, except very close to the surface of the star where the temperatures are lower. So in the interior, it is largely fully ionized plasma. So the primary processes that you really have there are Bremsstrahlung, and of course the Thomson scattering, or you can even say Compton scattering, between the electrons and the photons. So depending on the relative importance of these processes, you have to then find a weighted mean cross section here, interaction cross section. So that tells you how far a photon can propagate without interacting, basically. So 1 by n times sigma is the distance that, on an average, a photon can propagate without interaction. And after that, you would expect the interaction to definitely occur. So one has to get into the radiation processes and then find what is the rate of interaction of this between the photon and the electrons, and convert that to a cross section. So the cross section is nothing but the probability. It's related to the probability of interaction between a photon and the surrounding material. So to get the actual values of that, you'll have to go back to the radiation processes.
Okay, and there were a couple of questions, actually, I can lump them, related to degeneracy pressure. So someone asked, what is the force responsible for the degeneracy pressure? Another person asked, what species is providing the degeneracy pressure in brown dwarfs? So maybe you can lump those two together and answer.
Yeah. So the brown dwarfs, the degeneracy pressure comes from electrons.
And then the
pressure,
the other.
So the pressure is, you can think of pressure as momentum flux, right? So as long as there are particles which are moving, it is the kinetic energy of the particle which will provide pressure, right? So suppose you have a hose pipe and a lot of water is flowing through it. You construct a surface perpendicular to that flow, and that surface is going to feel a pressure, which is due to this motion of water. And similarly, when electrons are moving, they are providing pressure to their surrounding. This comes just from the kinetic energy of these electrons. So the momentum flux of this degenerate electrons gives you pressure. This can happen at 0 temperature. So that's the importance of it. In case of thermal pressure, again, it comes from the kinetic energy of the electrons. The pressure comes from the kinetic energy of the electrons. But the kinetic energy is coming because of the thermal excitation. So basically, the Maxwell-Boltzmann distribution of the energy of the electrons. On the other hand, for degeneracy pressure, even at 0 temperature, you have finite momentum of the electrons. And that is the source of pressure that we're talking about when we talk about degeneracy pressure.
Thanks. So a couple of related questions, perhaps. Actually, these are more on opacity and metallicity. Yeah. So one question is to explain a little more, I guess, the Kramer's opacity. So they're asking why you get the T to the 3/2 dependence.
Yeah.
And then there's one more I'd ask after you answer that one.
Yeah, so I was not going to do a derivation of this T to the 3/2. This has to do with the, so you have, for a given electron, the Bremsstrahlung cross section, or the Bremsstrahlung absorption rate, depends on the energy of the electron, depends on the speed of the electron. Now, for a given temperature, you have a whole distribution of electrons with its Maxwellian velocity distribution profile. So you have to first integrate over the population of the electrons the interaction probability. And then we do a second average of that probability over the energy distribution of the photons themselves, which is the Planckian energy distribution. And when you do both these averages, both of which have temperature in them, you end up with this expression of t to the power of 3.5 by rho squared. So the exact derivation of it, I do not have time or space to do over here, but I would refer you to maybe Rybak and Lightman's book on radiative transfer to see how, as was said, this is the Kramer's opacity, how that is derived from the basic principles of Bremsstrahlung radiation.
Thanks, Dipankar. A couple more questions in the meantime. So one is, what information about metallicity can we extract from the HR diagram?
This is well beyond what I'm going to cover in these lectures. But okay, the position of this main sequence, or the color of any given star on the main sequence for a given luminosity, depends on the metallicity. So the theoretical HR diagram, for example, as I showed, actually assumes a metallicity here. So if you have a different metallicity, the position of this main sequence will be different. So if you are able, for example, for a star cluster for which distances of all stars are known accurately, then and if you can construct the main sequence, the position of the main sequence will tell you something about the metallicity itself. So, so it is indeed a marker of metallicity, but usually it is done the other way around. You never get distances so accurately of star clusters, so you can measure the metallicity by spectroscopy and then define where the main sequence should be, and then use the observed main sequence to find the distance to the cluster. So, but yes, metallicity is important.
Yeah, actually, I have a follow-up that's kind of pretty interesting. So, is it when they look at a cluster, I mean, they detect some sort of average metallicity in the in the spectra of the brightest stars, or how is it, or is it sort of some surrounding gas? Okay.
No, it's the stars themselves. So the stars are the brightest sources of light. So you can easily take the spectra of them, even if it is a combined spectra of stars. So you can take the spectra and then you can look at the metal lines and the hydrogen lines and the helium lines, and then look at their ratios, and then that gives you a metallicity of the concentration of these different elements in those stars, and that gives you the metallicity.
Next question, a little bit technical on the technical side. So the question is, when M over R is large, the dPdr equation gets extra terms from GR and SR, as you showed in your slides. How does this? How do these relativistic terms affect the Virial theorem? That's the question.
The Virial theorem qualitatively is not affected, but quantitatively the coefficients and so on change, and the principle remains exactly the same. But we don't have this twice this, right? So what we had, yes. So these coefficients, this will not be twice anymore. This will be some large number. So it will vary. So this coefficient will have a M by R dependence. And for a neutron star, for example, this coefficient goes to more than 6 or something like that. So that is the extra effect that these terms will have. Now, other than that, the qualitative principle remains the same. So, for example, if you take a neutron star and then around that you consider its perturbations, expansion, contraction, and so on, you can still apply the same concept with a different coefficient.
Thanks. Okay, one question just popped up. I'm just reading verbatim. So we know that there are massive magnetic stars with a decent amount of angular velocity and relatively strong B field. How much do these factors contribute in structure evolution, specifically in context to the nuclear burning? So, and how much do velocity and B field affect?
Right. So magnetic fields in normal nuclear burning stars have not been shown to be strong enough to affect nuclear burning appreciably in the core. It can have strong surface magnetic fields. There are stars, for example, AM stars and so on, where the overall dipole magnetic field can be quite strong. It can affect the structure of the outer envelopes of the star, but the energy density of the magnetic field is still a small fraction of the energy density of the thermal gas as you go close to the center where the nuclear burning is occurring. So this is true also for radiation by and large. Radiation can, in principle, in some of these stars, be very fast at the center. And so such fast differential rotation with high angular speed near the center can, not so much in the main sequence, but in the late stages of nuclear burning, can cause some anisotropy at the center in the nuclear burning region. That can cause an additional convective type instability in the nuclear burning region. And these convective type instabilities can transport the nuclear burning energy more effectively to outer parts of the star. And in some cases, it has been thought that this kind of rotation is actually essential to really have a successful supernova explosion. Otherwise, it is not so easy to get the energy out. So in the late stages of nuclear burning, yes, particularly in terms of energy transport from the nuclear burning layer, rotation can have a significant consequence. Magnetic field, not so much. We haven't seen in the nuclear burning stages of normal stars, magnetic field to be of that higher strength, to be of dynamical importance. It becomes more dynamically important in compact stars.
I don't see anything popping up.
Yeah, so I can see one question in the chat box.
Yeah.
Says, which stars are treated relativistic?
Okay. Yes.
So by relativistic, I mean where the speeds of the constituent components are approaching the speed of light. So you can think of, let us say, degeneracy pressure supported configuration, degeneracy pressure coming from electron degeneracy pressure. Now, the Fermi momentum, okay, let me go to that slide. Yeah. Fermi momentum, as you can see, increases as number density of the electrons increase. So I can keep increasing the number density of electron. I can keep squeezing the configuration to higher and higher density. Then the PF will keep increasing. So as the value of the Fermi momentum approaches the rest mass of the electrons times the speed of light, then you'll begin to see a strong departure from this pressure law, and you'll approach this pressure law. and those are the stars which are called relativistic stars. Neutron stars, for example, have electrons in the highly relativistic state, but the neutrons and protons there are not quite relativistic. So again, we will see that in more detail as we go to the future lectures. Okay, two questions. I see that those stars which will not burn, what will they become? Not cloud, but they have already condensed from the cloud. So this is a self-gravitating bound configuration. We call them those which are held by degeneracy pressure. We call them brown dwarf. So stars which have not had nuclear burning, but have pressure support from electron degeneracy pressure are called brown dwarfs. As you go to lower pressures, there are other pressure support which can also occur. For example, Coulomb interaction. And those which are held by Coulomb interaction are called planets. So they're all the family of similar things. You call them by different names as to what is the support, source of support that against gravity that they have. So you have planets at low mass n, then you have brown dwarfs, and then you have stars. Okay, just to be clear, M1, M2, last plot refer to different types of stars like white dwarf and brown dwarfs, correct? Yeah, in this case, I have just kept M1, M2, M3 as different examples of masses, but I have drawn these in a manner to illustrate what different things can happen. M1, for example, in this diagram will end its life as brown dwarf. M2 will undergo hydrogen burning, and I have not shown the next nuclear burning stages. So it will go through some nuclear burning and it will end its life as a white dwarf. M3 is too massive to be supported by electron degeneracy pressure, so it cannot end its life as a white dwarf. So it will proceed to form either a neutron star or a black hole.
Okay. All right. So I think we are kind of nearing the end of the time. So I just want to be mindful of that.
Sure. And so, I think we have also the next 2 days.
Yeah. So maybe just one more question. I think I see questions on compact stars, which I think will come later. So just in keeping with the topics today, I'll just take, I think I'll just make this the last question. Is there any relation between bolometric magnitude and the B minus V magnitude that you showed?
Yeah. So in fact, I have put MV here. The better thing to do to construct a Hertzsprung-Russell diagram would be to put a bolometric magnitude, because that would give you a closer measure to total luminosity than MV is. So and it will have a similar, it has a similar structure where you can see main sequence and all the other branches of the Hertzsprung-Russell diagram. So bolometric magnitude versus V minus V will look very similar to this, with slight changes in shape. And of course, the overall scale, because bolometric luminosity will lift the numbers up a little bit. That's all.
Okay. All right. So I think we'll stop here. And thanks again, Dipankar. Thank you, everybody.
Thank you very much. Thank you all.
Thank you.